One of the most surprising recent discoveries in modern astronomy was the hot Jupiters found orbiting other stars. These are giant planets similar to Jupiter in our solar system, but where Jupiter is cold and orbits 5 times further from the Sun than the Earth, the hot Jupiters orbit more than 10 times closer to their host star than the Earth orbits the Sun. And, being so close to the star, they have very high surface temperatures. The first hot Jupiter was 51 Pegasus b, discovered by the Swiss astronomers Mayor and Culas in 1994, and many more have been discovered since.
Today, hot Jupiters are very well established. We know about 1% of stars have a giant planet orbiting around them once every 3 or 4 days. But that wasn't always the case. So when you first discover something, sort of by its nature, the discovery it's new. You're pressing the limits of science and you're stretching. And so the first discoveries are often not the most secure, right? We just barely detected the thing. And so it might be possible for something else to imitate a planet. So when astronomers announced the discovery of the first hot Jupiter, 51 Peg b, some astronomers were skeptical and asked, well, could this really be a brown dwarf? Other astronomers said, well, could it really be star spots on the star? And could those effects masquerade to explain the observations that astronomers had at the time? And so other astronomers observed the same star. Astronomers have searched different stars. We've done statistical analyses. We've done many different things to eliminate those various possibilities. And now we understand that 1% of stars have a hot Jupiter, and there's not a controversy about it anymore. But the nature of science is that when you first discover things, you fully expect other people to say, well, you have that data, you came up with one interpretation, can I explain another way? And that's a healthy part of the way science works.
As astronomers continued looking for planets around other stars, we found different varieties of planets, but the mystery of the existence of the hot Jupiters remained a puzzle that needed to be solved. How could a planet like Jupiter be buzzing around the surface of a star?
So the giant planets that orbit very close to their host star are typically discovered one of 2 ways. One is the Doppler effect, where we observe the light from the star, we spread it into a spectrum, and we measure the Doppler shift, the change of the color of that light very slightly, to determine that the star is moving towards and away from us. The other method that we use is the transit method, where a planet passes in front of the star, casts a shadow over the Earth, and we observe that the star appears to get a little bit fainter. And that allows us to see how big of a planet is passing in front of the star. Those 2 different methods are complementary. One measures the mass of the planet, the other measures its size. We like to combine those and learn things about the density when we can. And both those methods are best suited for finding planets close to their host star. So it's not too surprising if they are there. Some of the first planets we discover are close to their host star. What was really surprising is they're there in the first place. Even our method is most sensitive to finding planets very close to their star. If nature doesn't have them there, we look and we don't find them, right? So we're able to observe these hot Jupiters through either the Doppler or the transit method and see that they're there today. And that was surprising because we were thinking in the context of our own solar system, where Jupiter's out 5 times further from the Sun than the Earth is. Saturn's even further. But we found these giant planets 1/20th the distance from the Earth to the Sun. So very close star, just a few times the radius of the star, very, very close. And so that makes you wonder, well, how did they get there? Did they form there? And after a fair bit of thought, astronomers conclude, well, all the planet formation theories seem to say that if you want a planet that massive, you would need a humongous disk to be able to get all that matter so close to the star. And when we look at disks around other stars, they have mass that extends out hundreds of times further than that. And so you add up all that mass, and well, there'd be a disk bigger than the star, right? And so some things didn't quite make sense. And so, well, let's fall back onto our original ideas. Maybe Jupiter and Saturn are at distances where these giant planets form. We see their giant planets or other stars close. Is it possible they moved? And perhaps the somewhat surprising is actually astronomers had even predicted that giant planets should move, but they said that the mathematical calculations predicted they would migrate so quickly. It was clearly wrong. It couldn't be true. Jupiter and Saturn stay where they are today. And so when people first started exploring how rapidly these giant planets would interact with the disk, and they concluded that they should very rapidly spiral into the star, it was basically, well, something's wrong with that calculation. But now that we have observational evidence, there are some giant planets very close to their star. Well, okay, maybe that theory wasn't crazy after all. Maybe we need to revisit, look at the details, figure out, okay, is there a way that maybe it's not quite as fast as we visually envisioned? Is there a way that once it starts migrating, as it starts spiraling in through this disk, that it can occasionally stop, right? So if it keeps going all the way into the star, then the planet's gone and we don't see it. So not only do we need to understand how the planets started to spiral inwards, but once they've moved from 5 AU to 4 AU to 3 AU to 2 AU to 1 AU to a 10th to a 20th, why'd they stop then? Right? And that's one of the parts of the theory that astronomers are still struggling with, trying to understand what's the physical mechanism that allows that migration speed to slow down and eventually stop so close to their host star. And we have several ideas, but they're complex, and it's something that's not easy to test in a laboratory. The conditions are unlike the environment we have on Earth, and so we're still sort of struggling to understand, once they start migrating in, what causes them to stop.
If the planets migrate, if they move around from their place of birth, how do they do this? Understanding the process by which giant planets could be transported from the outer reaches of a planetary system down to near the surface of the star became a major goal for astrophysicists modeling the formation of extrasolar planets.
Well, but today our solar system has the sun at the center and has each of the 8 planets and the asteroids and everything else that basically orbit the sun, and it's mostly Newton's laws of gravity, the laws of motion, where the planets follow orbits and sort of a clockwork universe, where the planets follow an orbit that changes only very slowly, and they basically stay in their orbits for billions of years. But early in the history of the solar system and other planetary systems, those planets had to come from somewhere. There was gas, there was dust, there was pebbles, there were boulders, and the gas formed the dust that formed the pebbles that formed the boulders that became the cores that either became the Earth, Mars, Venus, sort of rocky planets, or became the core of the giant planets, Jupiter and Saturn, before they accreted hydrogen and helium to become so massive. So back when that disk was around, there was all this gas, and gas creates drag. So if you're in introductory physics class and you calculate everything about dropping balls and whatever, you always ignore air resistance, right? Because that makes calculations easy. But in real life, just as we have to take into account that bicycling fast is hard because of the wind resistance, these pebbles going through the solar system, when there's gas present, face a headwind. And that headwind slows them down. So in the early solar system, when we had gas present, the pebbles and boulders that are going to grow up to become these planets, and even the cores of the planets themselves, are facing a headwind. And just like if you're bicycling at high velocity, you feel the headwind, you're having to work hard to maintain your velocity. Well, that energy is being dissipated into that gas, heating the gas around it, and causing the planetesimal or planet to spiral inwards. And so as that happens, you have a mechanism to explain why do planets migrate inwards. Once they get really massive, things become even more complicated, because not only do they face a headwind, but the gravity of the planet starts to affect the disk. And so instead of just having a nice smooth disk and sort of going through a smooth amount of gas, our gravity is clearing out gaps and causing spiral wakes that are going to be shocks for other planets to pass through. And it gets much more complicated. And in some cases can slow down the migration a lot. If the planets accreted the nearby gas, so there's a gap in the disk, well, the headwind's not as strong. And so now that migration where it can slow down, and it can sort of move at the rate at which the disk evolves. So now you have the planet stuck in this gap, and as the gas dissipates energy all around the planet, that disk gradually accretes onto the star, and the planet moves in with it. And so these giant planets may have had 2 or more different stages of their migration history. First, a pretty simple headwind. Later on, more complicated gravitational interactions. that allowed them to migrate from the outer regions of the solar system that were cool and able to condense grains from a protoplanetary disk down into the hot regions where it's so hot that you wouldn't even be able to form solid silicon.
When there are two or more planets, the interaction of the planets can become important. A key phenomenon, resonant interactions, can continue shifting the planets' orbits around, strong enough that we can see the effect in the few years we have observed these systems. Yet resonances are simple as child's play.
So in a planetary system, you have different planets orbiting the star, and most of the time as they go around, they're pretty far apart. But every now and then, the planets line up. So there's star, one planet, the other, and that's the closest those planets are going to get to each other. And since gravity depends upon the distance between those two planets, that's when the gravitational influence is the strongest. So every time these planets pass next to each other, they get a little bit of a kick. Now, if those kicks are just sort of random, then the effect on the planets is relatively modest and maybe manifests itself over millions or billions of years, but it doesn't cause large changes in their orbits. On the other hand, if those little kicks all add up in the same way, they can have a big cumulative effect. So think about when a kid is on a swing. At first you stick them on the swing, they're just kind of sitting there, and maybe you tell them to kick their legs, they kind of swing, and they don't go anywhere. They kind of wobble around and go about as far as they can kick their leg. But after a while, that kid learns that if they manage to kick their legs once every time they go near the bottom, that instead of just wiggling at the bottom, they can go higher and higher. And so in the same way, if these little kicks that the planets get when they pass close to each other, if instead of being randomly arranged, if they're sequenced so that the different kicks progressively cause forces in the same directions, those little kicks can accumulate over hundreds, thousands, tens of thousands of years and cause much stronger interactions between these planets, so that we're able to see their effects not only over the course of the solar system's evolution, but within the decade that we've observed some of these planetary systems.